Imagine standing beneath a night sky so vast it makes you feel impossibly small until you remember every star up there holds secrets that could change everything down here. For centuries, the mysteries of space haven't just captivated us, they've rewritten the rules of life on Earth. Think about it, the telescope didn't just reveal planets, it shattered our understanding of the universe's scale. The discovery of cosmic radiation didn't just fill textbooks, it revolutionized medicine and energy. Every time we've dared to look deeper, space has handed us breakthroughs that ripple through our lives in ways we never saw coming. Now we're on the brink of another seismic shift. Scientists are uncovering wonders so profound they could redefine what it means to be human. From rogue planets with oceans hidden beneath their crusts to signals from the void that might not be cosmic static after all. This video isn't just a countdown, it's a portal to 30 discoveries lurking in the darkness right now, each with the power to alter our future. Picture ancient ice volcanoes on distant moons spewing ingredients for life, or black holes bending the fabric of reality in ways that could unlock interstellar travel. These aren't sci-fi fantasies, they're real, they're happening, and they're closer to touching your daily life than you think. What if the key to curing disease is floating in the atmosphere of a gas giant? What if the solution to climate change lies in the dust of a long-dead star? The universe is whispering answers to problems we haven't even solved yet, and today we're pulling back the curtain on the most jaw-dropping revelations. Whether it's a particle that could give us unlimited energy or a cosmic anomaly that challenges everything we know about time, these discoveries aren't just changing science, they're rewriting the story of us. So grab your curiosity like a spacesuit helmet and buckle up. The next chapter of humanity starts now. For decades, Mars was the dusty, barren neighbor we thought had given up its secrets until radar data pierced through the red planet's icy facade and revealed the unthinkable, vast lakes of liquid water hidden deep beneath the polar ice caps. This wasn't just a puddle or a trickle. These were reservoirs stretching over 12 miles wide, buried under nearly a mile of ice. The discovery sent shockwaves through the scientific community because water isn't just a resource, it's the universal currency of life. Every organism we know depends on it, which means those dark, briny pools could be the first chapter in an alien biology textbook. But here's where it gets even wilder. The water isn't frozen solid thanks to a cosmic twist. Mars' underground salts act like antifreeze, lowering the freezing point and keeping it liquid in conditions that would turn Earth's oceans to ice. That same salt could hold clues about the planet's volcanic past or even remnants of ancient microbial life. Scientists are already brainstorming how to probe these depths, with proposals ranging from robotic drills to melting probes that could taste the water for organic fingerprints. And let's talk about what this means for us. Water is the backbone of survival, not just for drinking, but for growing food, producing oxygen, and even making rocket fuel. Future colonists could literally split those water molecules into hydrogen and oxygen, the very ingredients needed to power return trips to Earth or voyages deeper into the solar system. Suddenly, Mars isn't just a destination, it's a cosmic gas station, a potential farm, and maybe even a second home. The technology that spotted these hidden lakes, a radar instrument called MARSIS on the European Space Agency's Mars Express orbiter, works like a planetary X-ray machine, bouncing radio waves through ice and rock to map what lies beneath. It's the same kind of tech we've used to find subglacial lakes in Antarctica, where life thrives in total darkness, proof that where there's liquid water, life might stubbornly follow. So what's next? Missions like NASA's Perseverance rover are already hunting for signs of past life in dried-up riverbeds, but the real jackpot lies in those buried lakes. The challenge: drilling through a mile of ice without contaminating what could be the first extraterrestrial ecosystem we've ever found. It's a delicate balance between exploration and preservation, but one thing's certain: Mars just got a lot more interesting. And if we're not alone in the universe, the answer might be waiting not in the stars, but right beneath our feet on the rusty soil of our planetary neighbor. While Mars tantalizes us with its hidden water, scientists are finding entire worlds beyond our solar system that could rewrite the definition of home. Imagine planets bathed in the gentle glow of alien suns, where oceans might lap against shores we've never seen. These aren't just specks of light in a telescope, they're real places, and some sit perfectly in what astronomers call the habitable zone, that sweet spot around a star where temperatures could allow liquid water to exist. Take the TRAPPIST-1 system 39 light-years away. It's a cosmic jackpot, 7 rocky planets orbiting a tiny, cool star with 3 squarely in that Goldilocks zone. One of them, TRAPPIST-1e, might have the right conditions for an ocean broader than Earth's Pacific. But here's the twist: because its star is so dim, the planet is likely tidally locked, meaning one side always faces the light while the other drowns in eternal night. That could create unimaginable weather patterns, with hurricane-force winds howling between scorching deserts and frozen wastes. Yet in the twilight border between these extremes, life might find a way. Then there's Kepler 452b, dubbed Earth's cousin, a world 60% larger than ours with a year 385 days long. It's spent 6 billion years in its star's habitable zone, twice as long as Earth, giving biology an enormous head start. Picture forests of towering alien flora or oceans teeming with creatures shaped by eons of calm, stable evolution. But how do we even find these distant gems? Tools like NASA, Kepler, and TESS telescopes use the transit method, detecting the faint dimming of a star as a planet crosses in front of it. It's like spotting a moth flying past a street lamp from miles away. Each dip in starlight reveals a world-size orbit and even hints about its atmosphere. The real game-changer, though, is the James Webb Space Telescope. Its infrared eyes can analyze the chemical fingerprints of exoplanet atmospheres, hunting for oxygen, methane, or industrial pollutants that might hint at civilization. Imagine the day we detect a sky tinged with pollutants not from volcanoes but from smokestacks. Yet the challenges are staggering. Even the closest habitable zone exoplanets would take thousands of years to reach with current technology. That's why scientists are racing to develop light sails, antimatter engines, and warp drive concepts that sound straight out of sci-fi. But so did moon landings a century ago. What's breathtaking isn't just that these worlds exist, but what they represent: proof that Earth isn't a lonely accident. The universe is practically shouting that places like ours are everywhere. And whether we ever set foot on them or not, that knowledge alone changes everything. For the first time in history, humanity can look up and point to actual dots on the map where our grandchildren's grandchildren might build their homes. The cosmos just got a lot more crowded and a lot more hopeful. Beneath the icy crust of Saturn's tiny moon Enceladus, a cosmic geyser erupts with secrets that could rewrite our search for life. When NASA Cassini spacecraft swooped through these glittering plumes, it didn't just find water vapor. It detected a buffet of organic molecules, the building blocks of every living thing we know. These weren't just simple carbon compounds. Cassini found complex chains like methane, propane, and even hints of amino acids, the very ingredients that on Earth form proteins and DNA. What makes Enceladus so extraordinary isn't just what's in its plumes, but where they're coming from. The moon hides a global ocean beneath 12 miles of ice, heated by Saturn's gravitational squeeze, creating hydrothermal vents on the seafloor, just like those in Earth's oceans where life thrives without sunlight. The plumes act like a celestial straw, sucking subsurface water and spraying it into space, giving us a free sample of what might be brewing below. It's as if the universe handed us a soda can, shook it up, and said, "Here, take a sip." Now imagine the implications. If life exists there, it wouldn't need sunlight or a friendly atmosphere, just chemistry, liquid water, and energy from those vents. Microscopic organisms could be floating in that dark ocean right now, completely unlike anything on Earth. Or maybe, just maybe, we're seeing the first stirrings of a second genesis, proof that life isn't a rare fluke but a cosmic inevitability. The next step, touching the water. Proposed missions like the Enceladus orbiter aim to orbit the Moon, analyzing plumes with advanced spectrometers, and even land near a vent to taste the ice for biosignatures, molecules only life could produce. There's talk of mini submarines that could melt through the ice, exploring an alien sea in real time. But the clock is ticking. Saturn's gravity is slowly shutting Enceladus's vents as the Moon cools, meaning this window to study a potentially habitable world won't stay open forever. For now, Cassini's data keeps scientists awake at night. One lingering mystery: the plumes contain hydrogen gas, a telltale sign of active hydrothermal chemistry, and on Earth, microbes eat hydrogen for breakfast. It's not proof of life, but it's the next best thing, a neon sign pointing to the most promising real estate in the solar system for finding neighbors. Enceladus isn't just another icy moon, it's a test tube for the universe's greatest experiment, and we might be just one mission away from cracking it open. In October 2017, astronomers spotted something streaking through our solar system that defied every expectation, a visitor from another star. They named it Oumuamua, Hawaiian for scout or messenger, and its oddities began piling up immediately. First, there was its shape. Unlike any asteroid or comet we'd seen, this thing was long and skinny, stretching perhaps 800 meters in length, but only 80 wide, like a cosmic cigar tumbling end over end through the void. Then came the real head-scratcher. Oumuamua accelerated as it left the sun's pull, something comets do when their ices vaporize, creating a visible tail. But this object showed no outgassing, no dust cloud, no hint of the activity that normally explains such movement. It was as if an invisible hand gave it a gentle push on its way out of the neighborhood. Cue the theories. Some scientists argued it might be a hydrogen iceberg, a chunk of frozen hydrogen gas evaporating in sunlight, except hydrogen ice isn't something nature is known to make in interstellar space. Others suggested it could be a fractal like dust bunny, a loose aggregate of particles with bizarre properties, but the most electrifying hypothesis came from Harvard astronomer Avi Loeb, who proposed Oumuamua might be artificial, a light sail fragment from an alien civilization, its flat surface catching solar radiation like a kite in the stellar wind. The backlash was swift. Mainstream science dismissed the alien tech idea as sensational, pointing out that extraordinary claims require extraordinary evidence. Yet the mystery endured. Even the most conservative models struggled to explain Oumuamua's acceleration without invoking some exotic, unseen mechanism. The object's reflectivity was another puzzle, 10 times shinier than a typical comet, as if coated in polished metal. What's haunting is that we'll never know for sure. Oumuamua is already beyond the reach of our telescopes, streaking toward the constellation Pegasus at 60,000 miles per hour. Future observatories like the Vera Rubin telescope might spot more of these interstellar interlopers, giving us a clearer picture. But for now, this celestial enigma serves as a humbling reminder. The universe is full of phenomena we haven't even begun to understand. Whether it was a weirdly shaped rock, a new kind of cosmic iceberg, or something even more unimaginable, one thing's certain: Oumuamua didn't play by our rules. And that's what makes it thrilling. Deep in the cosmos, there are flashes of energy so powerful they outshine entire galaxies, and they last less time than it takes to blink. These are fast radio bursts, or FRBs, some of the universe's most enigmatic signals. Picture this: a single millisecond pulse from billions of light years away carries as much energy as the sun emits in 80 years. And we still don't know what's causing them. What makes FRBs so baffling isn't just their intensity, it's their unpredictability. Some fire once and vanish forever, while others repeat in erratic patterns, like a cosmic Morse code we can't decipher. In 2020, scientists traced one repeating burst to a magnetar, a type of neutron star with a magnetic field 1 trillion times stronger than Earth's. These cosmic monsters twist space-time around them, and when their crusts snap under pressure, they might unleash these radio shockwaves. But here's the twist: not all FRBs fit this explanation. Some come from regions of space with no obvious source, leaving room for wilder theories, including the possibility, however slim, that we're catching whispers from advanced civilizations. Imagine an alien race harnessing the energy of a black hole to power interstellar beacons, or using FRBs as propulsion for light-sail spacecraft. It sounds like sci-fi, but the truth is we can't rule it out yet. That's the thrill of FRBs. They're either a natural phenomenon we've never seen before, or the first hint that we're not alone. But here's where it gets practical. FRBs aren't just cosmic curiosities, they're tools. As these bursts travel across the universe, they pass through clouds of ionized gas, which leaves fingerprints on their signals. By studying these distortions, astronomers can map the universe's hidden matter, the invisible scaffolding that holds galaxies together. It's like using a flashlight in a foggy room. The way the beam scatters reveals what's in the air. And then there's the space-time factor. Some FRBs arrive with a strange signature. Their high-frequency waves show up slightly earlier than low-frequency ones. This could be proof of quantum gravity effects, a missing piece in Einstein's relativity puzzle. If confirmed, it would mean FRBs aren't just messages from the cosmos, they're keys to unlocking physics beyond our wildest theories. The hunt for answers is heating up. Telescopes like CHIME in Canada scan the sky daily, catching dozens of new bursts, while projects like the Square Kilometre Array will soon listen with unprecedented sensitivity. Every new detection peels back another layer of the mystery. Whether they're stellar quakes, alien engineering, or something entirely unknown, FRBs remind us the universe is still full of surprises, and the next flash could change everything. Somewhere in the depths of space, an invisible force is playing tug-of-war with our entire galaxy, and winning. Meet the Great Attractor, a gravitational anomaly so massive it's dragging the Milky Way and thousands of neighboring galaxies toward it at 14 million miles per hour. Imagine a cosmic whirlpool hidden behind a curtain of dust. Its pull so relentless it bends the paths of galaxies like rivers flowing toward a waterfall. For decades, this mystery lurked in what astronomers call the zone of avoidance, an area near the constellation Centaurus where the Milky Way's own dust and stars block our view. It's like trying to study a lighthouse through a blizzard, but thanks to infrared and X-ray telescopes, we've peeled back the veil enough to glimpse the culprit. A colossal cluster of galaxies dubbed the Norma Cluster, surrounded by dark matter scaffolding weighing as much as 100,000 Milky Ways. Yet here's the twist: the Great Attractor isn't the end of the story. It's just a pit stop on a far grander journey. Beyond it lies an even more massive structure called the Shapley Supercluster, a gravitational titan pulling the Great Attractor itself. It's a cosmic matryoshka doll of influences, with each layer rewriting our understanding of how matter organizes itself across the universe. What makes this discovery earth-shaking isn't just the scale, it's the implications. The Great Attractor challenges the bedrock assumption that the universe's expansion should be smooth and even. Instead, we're seeing a cosmos clumped together in ways that hint at unknown forces or even flaws in Einstein's gravity equations. Some theorists speculate exotic phenomena like cosmic strings defects in space-time left over from the Big Bang could be contributing to these gravitational wrinkles. For astrophysicists, it's a gold rush of questions. Could dark energy, the mysterious force accelerating the universe's expansion, interact differently in these megaclusters? Are we seeing the fingerprints of a multiverse where neighboring universes tug at ours through gravity? Every new observation chips away at the mystery, with projects like the Dark Energy Survey and the upcoming Euclid telescope mapping these flows in unprecedented detail. One thing's certain, the Great Attractor isn't just a curiosity, it's a reminder that we're passengers on a galaxy hurtling toward the unknown. And as the next generation of telescopes pierces deeper into the zone of avoidance, we might find that the true architect of this cosmic dance is stranger than anything we've dared to imagine. Picture holding a flashlight in a pitch-black cathedral. You can't see the walls, but the way light bends around unseen pillars reveals their shape. That's essentially how astronomers built the first three-dimensional map of dark matter, the universe's most elusive architect. Using a phenomenon called gravitational lensing, where massive objects warp space-time and distort light from distant galaxies, researchers stitched together a cosmic blueprint of this invisible substance. The result, a sprawling, filamentary web stretching across billions of light-years, confirming dark matter isn't just sprinkled randomly, it forms the hidden skeleton of the cosmos. What's astonishing is how much this map contradicts what we see with our eyes. The stars and galaxies we admire are mere decorations clinging to this underlying scaffolding. Dark matter outweighs visible matter 5-to-1, meaning everything we've ever touched, from mountain ranges to smartphones, accounts for less than 20% of the universe's total material. The rest is this enigmatic shadow, silently dictating where galaxies cluster and how fast they spin without emitting a single photon. But why does this matter for us? Because unlocking dark matter's secrets could ignite technological revolutions. Imagine materials engineered to interact with it, offering propulsion systems that harness gravitational anomalies for spacecraft. Or medical imaging that peers through obstacles by detecting dark matter's subtle gravitational whispers. Some theorists even speculated could be linked to extra dimensions, an idea once relegated to fringe physics now gaining traction thanks to these maps. The method behind this breakthrough is equally mind-bending. Teams used the Hubble Space Telescope and ground observatories to study light from 10 million galaxies, tracking how their images stretched and twisted as they passed through dark matter's gravitational field. Supercomputers then reconstructed these distortions into a three-dimensional model, like tracing the outline of a sculpture by studying its shadow from every angle. Yet mysteries remain. We still don't know what dark matter is, whether it's undiscovered particles, primordial black holes, or something entirely outside our theories. Projects like the Large Synoptic Survey Telescope aim to refine the map, while experiments deep underground hunt for dark matter particles through ultra-sensitive detectors. Every clue brings us closer to rewriting the rules of physics, energy, and perhaps even reality itself. The takeaway: dark matter isn't just a cosmic ghost story. It's the unseen hand shaping our universe's destiny, and soon it might shape ours too. On September 14, 2015, a ripple passed through Earth so subtle it warped the entire planet by less than the width of an atom. And in that tiny shudder, humanity cracked open a new window on the universe. The Laser Interferometer Gravitational Wave Observatory, or LIGO, had just captured the first direct evidence of gravitational waves, the cosmic vibrations predicted by Einstein a century earlier. The source, two black holes, each roughly 30 times the mass of our Sun, spinning around each other hundreds of millions of light years away before colliding in a cataclysm so violent it momentarily outshone every star in the observable universe combined. This wasn't just a breakthrough, it was a paradigm shift. For the first time, we weren't just seeing the cosmos, we were hearing it. Gravitational waves are the soundtrack of the universe, generated when massive objects accelerate, sending distortions through the very fabric of spacetime like ripples on a pond. Black hole mergers are particularly loud, producing a signature chirp as the two objects spiral inward, followed by a resonant ring down as the newly merged black hole settles into its stable form. The LIGO detection matched Einstein's equations with astonishing precision, proving that spacetime isn't just a static stage, it's a dynamic, vibrating medium. But here's where it gets groundbreaking. Every electromagnetic signal, light, radio waves, X-rays, gets scattered or absorbed as it travels across the universe. Gravitational waves pass through everything unimpeded, offering a pristine signal from events we could never otherwise witness. It's like swapping a foggy windshield for crystal-clear glass. Already, LIGO and its European counterpart Virgo have detected dozens of mergers, including one between neutron stars that solved a century-old mystery about the origin of heavy elements like gold and platinum. The technology behind this achievement is just as mind-bending as the discoveries. LIGO twin detectors, separated by 3,000 kilometers, use lasers bouncing through 4-kilometer-long vacuum tunnels to measure space-time distortions smaller than 1/10,000th the width of a proton. To put that in perspective, it's like measuring the distance to the nearest star with an accuracy of one human hair. Future upgrades and new observatories like Japan's Kagra and India's planned LIGO India will turn this into a global network, pinpointing cosmic collisions with GPS-level precision. What's next? Scientists are hunting for even wilder signals, primordial gravitational waves from the Big Bang itself, or the hypothetical cosmic strings that could be defects in the universe's fundamental structure. There's even speculation that advanced civilizations might manipulate black holes as energy sources, creating artificial waves we could detect. For now, every chirp and ring down adds a new note to our growing cosmic symphony, proving that sometimes the most profound truths aren't seen or touched, but felt in the silent stretching of spacetime itself. Beneath Europa's cracked, icy shell lies an ocean so vast it holds twice the water of all Earth's seas combined, a dark, salty abyss where no sunlight has ever penetrated. This isn't just another frozen moon, it's one of the most promising places in our solar system to hunt for alien life. The surface tells the story, fractures and ridges crisscrossing the ice like a global jigsaw puzzle, evidence of the liquid ocean beneath flexing and shifting under Jupiter's gravitational pull. But what's truly electrifying is what's happening at the seafloor. Just like Earth's deep-sea hydrothermal vents, Europa's hidden ocean could be bubbling with geothermal activity, spewing minerals and heat into the water, a recipe for life as we know it. NASA Galileo spacecraft first gave us clues in the 1990s, detecting a bizarre magnetic field around Europa that suggested a conductive fluid, likely salt water, sloshing beneath the ice. Then came the Hubble Space Telescope's bombshell, plumes of water vapor erupting from the Moon's south pole, shooting over 100 miles into space. It was as if Europa were offering us a taste of its ocean for free. When scientists analyzed the composition of those plumes, they found not just water, but salts and organic molecules, the very ingredients that on Earth feed entire ecosystems in the darkest depths of our oceans. Now the stage is set for NASA Europa Clipper, set to launch in 2024. This isn't just another orbiter, it's a purpose-built alien ocean detective. Armed with ice-penetrating radar, it will map the thickness of Europa's frozen crust, hunting for the thinnest spots where future missions might drill. Its mass spectrometer will sniff those water plumes for complex organic molecules, while its thermal imager scans the surface for hotspots where warm water might be welling up from below. But the most tantalizing tool, a magnetometer to measure the ocean's salinity and depth, because the saltier and deeper the water, the better the chances it's interacting with a rocky seafloor, creating the chemical cocktail life craves. The implications are staggering. If Europa's vents host microbes or something far stranger, it would prove life isn't confined to the cozy, sunlit pockets of the universe. It could thrive anywhere there's liquid water, energy, and chemistry, even in the perpetual night of an ice-covered ocean. That would mean countless worlds across the galaxy could be hiding similar secrets, turning the search for extraterrestrial life from a hopeful quest into a statistical certainty. Yet Europa isn't giving up its mysteries easily. Drilling through miles of ice to reach the ocean remains a colossal engineering challenge, one that might require nuclear-powered cryobots to melt their way down. There are ethical questions too: how to explore without contaminating a potentially pristine ecosystem. But with every flyby, every plume sample, we're peeling back the layers of this cosmic onion. Europa isn't just a moon, it's a test case for whether life is a cosmic fluke or a universal imperative, and the answer might be lurking right there in the dark under the ice. Late one August night in 1977, an Ohio State University radio telescope picked up a signal so extraordinary that the astronomer reviewing the data scrawled, "Wow." In red pen across the printout, a name that would echo through history. For 72 seconds, a burst of radio waves 30 times stronger than background noise blared from the direction of the constellation Sagittarius, matching the exact frequency scientists predicted an extraterrestrial transmission might use: 1420 MHz, the vibration frequency of hydrogen, the universe's most abundant element. Then, just as suddenly as it appeared, it vanished, never to be detected again. Decades later, the WOW signal remains the most tantalizing maybe in the search for extraterrestrial intelligence. What sets it apart isn't just its strength, but its uncanny precision. The signal occupied a narrow band of the radio spectrum, with no natural cosmic phenomenon known to produce such a clean, focused emission. It wasn't the static crackle of a pulsar or the smear of interstellar gas. It was a laser-like beam, the kind you'd expect from an intentional broadcast. And here's the spine-tingling part. The frequency it used can't penetrate Earth's atmosphere from the ground, meaning if it wasn't a satellite or aircraft, it likely came from beyond our planet. Yet the skeptics have their say. Some argue it could have been a reflected terrestrial signal bouncing off space debris, or an undiscovered comet's hydrogen cloud glowing in radio wavelengths. Others point out that a genuine alien transmission should have repeated either as a continuous beacon or a patterned series. But what if we caught just a fleeting fragment? Imagine a civilization's planetary radar sweeping across space like a lighthouse beam, briefly illuminating Earth before rotating away. Or consider the possibility that the signal was never meant for us at all, but was a misdirected whisper from some interstellar communication we stumbled upon mid-conversation. The impact of confirming such a signal today would be seismic. Projects like Breakthrough Listen now scan millions of frequencies simultaneously, using AI to filter out interference. If we found another WOW-like signal, especially one repeating or encoding mathematical patterns, it would prove we're not just hunting shadows. That moment would shatter our cosmic solitude, forcing us to confront questions we've only debated in fiction. How do we respond? What if they're long gone by the time we hear them? And most unnerving of all, if the universe is teeming with life, why does it feel so silent? The WOW signal's legacy isn't just about aliens, it's a lesson in humility. For all our telescopes and algorithms, the cosmos could be shouting at us in ways we're still too primitive to comprehend. Until the next signal comes, if it ever does, that lonely WOW on a piece of yellowed paper remains both a monument to our curiosity and a reminder. Sometimes the universe's most profound answers are the ones that refuse to repeat themselves. In the constellation Cygnus, a star unlike any other flickers like a faulty street lamp, dimming unpredictably by up to 22%, then brightening again with no rhythm or reason. This is KIC 8462852, better known as Tabby's star after astronomer Tabitha Boyajian, who first flagged its bizarre behavior. When NASA Kepler Space Telescope caught these erratic dips in 2015, they defied every known explanation. Stars don't just dim like this unless something massive is passing in front of them. But this wasn't the tidy, periodic shadow of an orbiting planet. It was as if the star were being swallowed by a swarm of shadows, each blotting out its light in chaotic, jagged patterns. Theories exploded like supernova. Could this be evidence of an alien megastructure, a Dyson swarm, a hypothetical array of energy-harvesting satellites built by an advanced civilization? The idea wasn't entirely fringe. Natural explanations failed at first. Not comets, not planets, not even a rogue black hole's accretion disk matched the data. But the megastructure hypothesis, while thrilling, was a last resort. Science demands we exhaust the ordinary before invoking the extraordinary. Then came the dust. Sophisticated follow-up studies revealed that the dimming wasn't uniform across all light wavelengths, a telltale sign of fine particles scattering certain colors more than others. The culprit, a vast, uneven cloud of cosmic dust, possibly from a shattered planet or colliding asteroids, drifting in a lopsided orbit around the star. But even this explanation left puzzles. The dust would need replenishing constantly to sustain the observed dimming over years, suggesting an ongoing cataclysm in Tabby's star system. What makes this mystery so transformative isn't just the star's odd behavior. It's how it's reshaping astronomy. Tabby's star taught us to expect the unexpected, training telescopes to monitor thousands of stars for similar anomalies. Already, others have surfaced. Epic 24671347 in Leo, V1333 in Lyra, each with its own fingerprint of bizarre dimming. Some may turn out to be interstellar dust storms. Others might reveal entirely new astrophysical phenomena like evaporating planets or crescent-shaped debris disks. The real breakthrough came when astronomers realized these erratic stars could be natural laboratories for studying cosmic dust's behavior under extreme conditions. Dust isn't just space static, it's the raw material for new planets, the smoke left behind by dying stars, and a key ingredient for life's chemistry. Understanding how it clumps, drifts, and obscures light in systems like Tabby's could help us interpret data from distant exoplanets, ensuring we don't mistake a swirling dust cloud for signs of life. For now, Tabby's star keeps its secrets, but whether the answer lies in crumbling moons, interstellar soot, or something even stranger, this cosmic oddity has already done something remarkable. It's reminded us that the universe still holds wonders no one's thought to imagine yet. And sometimes, the most profound discoveries begin with a single, inexplicable flicker in the dark. In the stark silence of deep space, a dead star spins faster than a kitchen blender. 50,000 revolutions every second, blasting the cosmos with beams of radiation so intense they'd vaporize a planet in seconds. Yet here's the cosmic plot twist. Around this celestial zombie, the first planets ever discovered beyond our solar system somehow cling to existence. Meet PSRB 1257 plus 12's planetary system, a family of worlds orbiting a pulsar, the crushed core of a once mighty star that went supernova and forgot to die quietly. The discovery in 1992 shattered every expectation. Planets weren't supposed to survive supernova. The explosions that create pulsars unleash enough energy to rip apart entire solar systems. But these worlds defied the odds, likely forming from the ashes of the catastrophe itself. Picture this: when the progenitor star exploded, much of its material was blasted into space, but some fell back into orbit around the newborn pulsar. Over time, this debris coalesced into new planets forged in the ultimate cosmic pressure cooker. The result: 3 nightmarish worlds where a teaspoon of matter weighs as much as a mountain, bathed in constant torrents of X-rays and gravity so strong it distorts time itself. The innermost planet, dubbed Draugr, is particularly eerie. Smaller than our moon, it completes an orbit every 25 days while enduring radiation bursts that strip away any conceivable atmosphere. Further out, Poltergeist and Phobter, named after malevolent spirits, endure slightly gentler conditions. If a gentle can describe temperatures swinging between molten metal days and cryogenic nights. What's astonishing isn't just that they exist, but what they reveal about planetary resilience. If worlds can form in the wreckage of a stellar explosion, then planet building might be far more adaptable than we thought, happening not just in placid nurseries of gas and dust, but in war zones of the cosmos. Pulsar planets also offer a gruesome preview of Earth's ultimate fate. When our sun dies 5 billion years from now, it won't go supernova, it's too small, but the idea that planets might persist or even resurrect around its corpse is both haunting and hopeful. Could life emerge again on a second-generation world, evolving in the glow of a spinning stellar cinder? It's a long shot, but these discoveries force us to expand our imagination. The real magic lies in how astronomers found them. Pulsars are nature's most precise clocks, their beams arriving on Earth with metronomic regularity. Any orbiting planets cause tiny wobbles in these signals, detectable only through nanosecond variations in the pulsar's rhythm. It's like listening for a fly's footsteps by how they disrupt the ticking of a grandfather clock. This method, called pulsar timing, opened a new frontier in planet hunting, one that later paved the way for techniques used by Kepler and TESS. While we'll probably never visit these irradiated wastelands, their lessons are universal. They prove planets can form in the most hostile environments imaginable, raising tantalizing possibilities. Could pulsar planets exist throughout the galaxy, invisible to most telescopes? Might some even harbor extremophile life in subsurface oceans, protected by miles of radiation-shielding crust? For now, these dead star worlds remain a testament to the universe's stubborn creativity, where even in death, new beginnings emerge from the ashes. The universe is unimaginably vast, with 2 trillion galaxies, each hosting billions of stars, many encircled by planets in habitable zones. Statistically, we shouldn't be alone. So where is everybody? This is the Fermi paradox, a haunting question posed by physicist Enrico Fermi over lunch in 1950. If intelligent life is probable, why haven't we found a single whisper of its existence? The silence speaks volumes, and the theories attempting to explain it range from sobering to spine-chilling. One leading explanation is the Great Filter, a hypothetical barrier so insurmountable that it prevents life from advancing to interstellar civilization. The terrifying possibility we might not have passed it yet. This filter could lurk in our future. Maybe artificial intelligence wipes out civilizations before they can spread, or advanced technology inevitably leads to self-destruction. Alternatively, the filter could be behind us. Perhaps the leap from simple chemistry to self-replicating life is astronomically rare, making Earth a cosmic fluke. But not all solutions are doom-laden. Some suggest we're simply too early, that the universe only recently cooled enough for complex life, and we're among its pioneers. Others argue advanced civilizations might avoid broadcasting their presence, adhering to a galactic zoo protocol where Earth is intentionally left undisturbed for observation. There's even the eerie possibility that they're here, but their technology is so advanced it's indistinguishable from nature. The paradox also forces us to confront our own trajectory. Every failed attempt to detect alien signals, like SETI decades of silent radio telescopes, sharpens the question, are we special or are we doomed? If the Great Filter lies ahead, our window to colonize other worlds might be closing. But if it's behind us, humanity could be destined to inherit the stars. What's certain is this: the Fermi paradox isn't just about aliens. It's a mirror reflecting our place in the cosmos, and a challenge to survive long enough to solve it. In March 2014, scientists operating a telescope at the South Pole made a discovery so profound it sent shockwaves through cosmology. The BICEP 2 telescope, a microwave observatory buried under the Antarctic ice, had detected faint spirals in the oldest light in the universe, the cosmic microwave background radiation. These swirling patterns were more than just cosmic static. They were gravitational fingerprints from the birth of spacetime itself, evidence that the universe expanded faster than light in its first trillionth of a second. This was the smoking gun for cosmic inflation, a theory first proposed by Alan Guth in 1980 that suggested the universe didn't just grow after the Big Bang. It exploded outward in an unimaginable growth spurt, stretching from subatomic size to cosmic scales in less time than it takes light to cross a single proton. What makes this discovery so groundbreaking isn't just the validation of inflation, it's the scale of the implications. Those faint spirals in the microwave background are ripples in spacetime, created by gravitational waves unleashed during inflation's violent expansion. Think of it like finding fossilized footprints in billion-year-old mud. The depth and shape tell us not just that something passed by, but how heavy it was and how fast it moved. The strength of these ripples suggests inflation was driven by energies 100 trillion times hotter than the Large Hadron Collider's most powerful collisions, a realm where gravity and quantum mechanics collide in ways we still don't fully understand. But here's where it bends reality even further. If inflation happened once, there's no reason it couldn't happen again or be happening right now in some distant pocket of space. This is the multiverse hypothesis. Our universe might be just one bubble in a frothing cosmic sea of eternally inflating regions, each with its own laws of physics. Some could have stronger gravity, making stars burn out in seconds. Others might lack dark energy, collapsing back into singularities before life can emerge. It's a dizzying thought. What we call the universe could be a speck in a far vaster, stranger cosmic landscape. The BICEP 2 findings also solved a mystery that had plagued cosmologists for decades: why the universe looks so uniform in every direction. Without inflation, there's no way heat and light could have spread evenly across billions of light years unless, as the data now suggests, everything we see was once crammed into a space so tiny that it had time to even out before inflation blasted it apart. This would explain the eerie consistency of the cosmic microwave background, where temperature variations are less than 1 part in 100,000. Yet the story isn't without controversy. Initial excitement about BICEP 2's results was tempered when follow-up studies suggested some of the signal might actually be interference from galactic dust. But even with those caveats, the broader case for inflation remains strong, supported by multiple lines of evidence, including the precise distribution of galaxies and the universe's flat geometry. Future telescopes like the Simons Observatory and CMB-S4 will peer even deeper into this primordial echo, hunting for finer details that could reveal inflation's exact energy scale and perhaps even hints of what triggered it. What's at stake isn't just a chapter in a physics textbook. If inflation is real, it rewrites the origin story of everything. The Big Bang wasn't the beginning, it was the aftermath. Our entire observable universe could be a speck in an endless cascade of inflationary events, each spawning new worlds with alien physics. For all we know, the answers to gravity's quantum secrets or dark energy's mystery might lie not in our cosmos, but in the untouchable bubbles beyond it. And that's the true legacy of BICEP 2. It didn't just glimpse the universe's infancy, it opened a doorway to realities we're only beginning to dream of. Methane shouldn't exist on Mars, at least not in the amounts we're finding. This simple molecule, made of 1 carbon atom and 4 hydrogen atoms, lingers in the Martian atmosphere in tantalizing bursts that defy easy explanation. On Earth, 95% of methane comes from living organisms, everything from bacteria in wetlands to the digestive tracts of cows. The rest is released by geological processes like volcanic activity or chemical reactions in rocks. But Mars, with its cold, thin atmosphere and seemingly dormant geology, shouldn't be producing methane at all. Yet NASA Curiosity rover has sniffed out repeated spikes of the gas in Gale crater, some exceeding background levels by 10 times. These aren't random fluctuations, they follow seasonal patterns, peaking in the Martian summer and vanishing in winter. It's as if the planet itself is breathing. The debate over where this methane comes from splits scientists into two camps. Team biology points to the eerie parallels with Earth's microbial methane producers. Subsurface bacteria, shielded from harsh surface radiation, could be metabolizing hydrogen or carbon dioxide, exhaling methane as a byproduct. If true, this would mean life isn't just possible on Mars, it's thriving right now beneath our robotic explorers' wheels. But team geology counters with equally compelling arguments. Certain minerals, like olivine, can react with water and carbon dioxide to produce methane through a process called serpentinization. Mars might also harbor hidden pockets of ancient methane, trapped in ice like compounds called clathrates that occasionally vent when temperatures rise. The mystery deepens when you consider how quickly the methane vanishes. Orbiting probes like Europe's ExoMars Trace gas orbiter often fail to detect the same plumes Curiosity finds on the surface. This suggests something, possibly ultraviolet radiation or reactive chemicals in the soil, is destroying the methane within weeks. That rapid destruction only heightens the intrigue. Whatever's producing it must be active and ongoing, not some ancient relic. The implications are staggering. If microbes are the source, Mars could be harboring life that evolved independently of Earth, a second Genesis in our cosmic backyard. Even if geology is the culprit, it hints at active hydrothermal systems or volcanic vents beneath the surface, reshaping our understanding of Mars as a dead world. Future missions like NASA Mars Life Explorer aim to drill deeper than ever before, hunting for isotopic fingerprints in the methane that could reveal its origin. Carbon from biological processes tends to be lighter, while geological methane often carries heavier isotopes. For now, the red planet keeps its secrets. But whether the answer lies in subterranean microbes or exotic chemistry, one thing's clear: Mars is far more alive than we ever imagined. And with every whiff of methane, it's whispering clues we're just beginning to decipher. At the frozen edges of our solar system, something massive is tugging at the fabric of our cosmic neighborhood, a shadowy gravitational hand reshaping the paths of distant icy worlds. This is the hunt for Planet 9, a hypothetical giant up to 10 times heavier than Earth, lurking 20 times farther from the Sun than Neptune. The clues: a cluster of Kuiper belt objects, icy leftovers from the solar system's formation, all mysteriously tilted in their orbits as if herded by an unseen shepherd. Their elongated paths point like cosmic arrows toward the same patch of sky, a pattern so unlikely to occur naturally that astronomers give it odds of just 0.2%. The math behind this phantom planet reads like a celestial detective story. In 2016, Caltech researchers Konstantin Batygin and Mike Brown noticed 6 distant objects with orbits tilted 30 degrees downward from the solar system's plane, a statistical fluke unless something massive was aligning them. Computer simulations revealed only one plausible culprit: a super-Earth or mini-Neptune on a slanted, elliptical orbit spanning 10 to 20,000 years. Its gravitational pull would explain not just the clustered orbits but another puzzle: why some Kuiper belt objects orbit backward against the solar system's flow. But finding Planet 9 is like searching for a black cat in a coal cellar. At such extreme distances, even a giant planet reflects virtually no sunlight, making it 1,000 times fainter than Pluto. Current searches rely on blink and you'll miss it movement in time-lapsed images from telescopes like Subaru in Hawaii and the Vera Rubin Observatory still under construction in Chile. There's an added twist: if Planet 9 exists, it might not be a traditional ice giant. Some theories suggest it could be a primordial black hole, a grapefruit-sized remnant of the Big Bang whose gravity mimics a planet's. The implications of discovery would rewrite solar system history. A planet this far out couldn't have formed in place. It would need to have been hurled outward by a young Jupiter's gravitational slingshot or even captured from another star. Its existence might explain other anomalies, like the Sun's slight tilt relative to the planets. For now, the hunt continues, with every oddball Kuiper belt object adding weight to the case. Whether it's a rogue world, a cosmic ghost, or just an extraordinary coincidence, one thing's certain: our solar system's story isn't finished yet. Imagine the energy of 1,000,000,000,000 suns packed into a single point of light, so brilliant it outshines every star in its home galaxy combined. That's the staggering power of a quasar, the universe's ultimate cosmic lighthouse. These celestial beacons were first mistaken for nearby stars in the 1950s, until astronomers realized their light was coming from the edge of the observable universe, racing toward us for billions of years. Today, we know quasars are the ravenous hearts of distant galaxies, where supermassive black holes weighing billions of times our sun's mass devour entire stars while blasting out jets of radiation visible across the cosmos. What makes quasars so transformative isn't just their spectacle, it's what they teach us about galactic adolescence. Every massive galaxy, including our Milky Way, likely hosted a quasar in its wild youth, fueled by a gorging black hole. As these monsters consume surrounding gas and dust, friction heats the material to millions of degrees, creating a swirling disk so luminous it lights up the galaxy like a bonfire. But here's the twist: quasars don't just destroy, they shape. Their intense radiation and particle winds act like cosmic sculptors, blowing away excess gas that would otherwise form stars, effectively putting a brake on their galaxy's growth. This delicate balance between creation and destruction helps explain why some galaxies stop making new stars billions of years earlier than others. The physics around quasars bends reality itself. Their accretion disks spin at near-light speeds, warping spacetime so severely that light can orbit the black hole like a planet circles a star. Some quasars fire jets of plasma hundreds of thousands of light-years into space, longer than the Milky Way's diameter, moving at 99.9% the speed of light. These jets are nature's particle accelerators, generating energies the Large Hadron Collider can only dream of. In fact, one quasar's beam holds the record for the universe's most powerful natural engine, pumping out enough energy every second to power human civilization for 100 trillion years. Yet quasars also hold clues to the universe's biggest mysteries. Their light, filtered through vast cosmic distances, carries chemical fingerprints of everything it passes, like a flashlight shining through fog. By analyzing these absorption lines, astronomers have mapped the distribution of intergalactic hydrogen, uncovering the universe's large-scale structure. Some quasars even act as time capsules. Their light, emitted when the universe was just a tenth of its current age, reveals how the earliest galaxies were built. The most unsettling revelation: quasars prove supermassive black holes grew impossibly large, impossibly fast. Recent discoveries show fully formed quasars existing just 600 million years after the Big Bang, too soon for conventional growth models. Some theories suggest they formed directly from collapsing primordial gas clouds, skipping the star phase entirely. Others speculate they're evidence of exotic physics, like wormholes funneling matter from other universes into ours. As our telescopes peer deeper, quasars keep rewriting the rules. The James Webb Space Telescope is now spotting hundreds of these cosmic monsters in the universe's infancy, challenging our timelines of galactic evolution. And with every new quasar found, we're not just witnessing the universe's most violent phenomena. We're decoding the blueprint of how galaxies, including our own, learn to live with the monsters at their cores. In the late 1980s, as NASA engineers tracked the twin Pioneer spacecraft hurtling toward the edge of the solar system, they noticed something bizarre: both probes were slowing down slightly more than physics predicted. This wasn't a glitch or a gust of solar wind. It was a persistent, unaccountable deceleration, as if an invisible hand were gently tapping the brakes. Dubbed the Pioneer anomaly, this tiny discrepancy, just 300 billionths of a meter per second squared, might seem insignificant, but in the precise world of orbital mechanics, where a single misplaced decimal can send a probe veering off course, it was a screaming red flag that our understanding of gravity might be incomplete. For decades, the anomaly defied explanation. Some theorized it could be evidence of dark matter's gravitational tug, a hidden halo of exotic particles dragging on the spacecraft as they ventured farther from the Sun. Others proposed a more mundane culprit, heat. The Pioneer's plutonium-powered generators emitted warmth, and even the faintest thermal radiation pushing against the probe's dish antennas could, over years, account for the drift. But when scientists meticulously modeled every photon bouncing off the spacecraft surfaces, the math still didn't add up. The discrepancy hinted at something deeper, a flaw in Einstein's general relativity, perhaps, or a previously unknown force acting at the solar system's icy fringes. What makes the Pioneer anomaly so tantalizing isn't just the mystery itself, but what it represents. Physics thrives on predictability. When reality deviates from theory, even by a whisper, it's often the first clue to a revolution. The anomaly echoed history's greatest scientific pivots, like Mercury's wobbly orbit, which couldn't be explained until Einstein rewrote gravity. Could Pioneer's slowdown be a similar cosmic breadcrumb? The case took another twist when later missions, like New Horizons, failed to exhibit the same anomaly. This suggested the effect might be unique to the Pioneer's design, but even that raised questions. If thermal radiation or onboard systems were responsible, why didn't other spacecraft with similar power sources show identical behavior? The inconsistency only deepened the intrigue, leaving scientists to wonder whether they'd stumbled upon a new gravitational phenomenon that only manifests under specific, still unknown conditions. Today, while most researchers attribute the anomaly to asymmetric heat radiation, the debate isn't entirely settled. The Pioneer's faint signal faded entirely by 2003, cutting off further data. But their legacy endures as a cautionary tale, a reminder that even our most trusted equations might harbor hidden exceptions. Whether the answer lies in undiscovered physics or something as simple as a warm metal panel, one lesson is clear. Sometimes the universe's quietest whispers hold its loudest challenges. Among the faint afterglow of the Big Bang, the cosmic microwave background radiation that blankets the entire sky, there's an anomaly so chilling it defies conventional explanation. Known as the cold spot, this mysterious region stretches a staggering 1.8 billion light-years across, registering significantly colder than its surroundings. It's not just a statistical blip. The odds of such a feature appearing randomly are less than 1 in 50. Something colossal left its mark here, and the leading theories sound like they're ripped straight from the pages of a multiverse thriller. At first glance, the cold spot seems like it could be a vast cosmic void, an underdense region where fewer galaxies and less matter scatter the CMB's photons, making it appear cooler. But when astronomers mapped the distribution of galaxies in this direction, they found the void explanation falls short. The scale of the temperature drop is too extreme for known physics to account for unless we're missing a fundamental piece of the puzzle. That's where things get wild. Some cosmologists suggest this could be evidence of a collision with another universe, a bubble from an alternate reality brushing against our own during the early moments of cosmic inflation. Picture two soap bubbles floating in a sink, their surfaces barely touching. The cold spot might be the bruised remnant of that contact, a cosmic fingerprint from beyond our spacetime. But there's another spine-tingling possibility. The cold spot could be the imprint of a cosmic defect, a crack in the universe's structure left over from its phase transitions in the first fractions of a second after the Big Bang. These defects, called textures, are theoretical knots in spacetime that formed as the fundamental forces of nature split apart during the universe's rapid cooling. If one of these textures unraveled in the early cosmos, the energy released could have created a lasting cold imprint in the CMB, like a scar from the universe's infancy. The stakes of solving this mystery couldn't be higher. If the cold spot truly is evidence of a multiverse, it would revolutionize our understanding of reality itself. Suddenly, the Big Bang isn't a singular event but one of countless bubbles in an eternally inflating megaverse, each with its own laws of physics. Such a discovery would place humanity in a humbling new cosmic context, not at the center of creation, but adrift in a frothing ocean of alternate realities. Even if the explanation turns out to be a rare but natural fluctuation, the cold spot forces us to confront how much we still don't understand about the universe's largest structures and their origins. What's next? Telescopes like the Simons Observatory and next-generation CMB experiments aim to scrutinize this anomaly with unprecedented precision, hunting for subtle patterns in polarization that could reveal whether the cold spot was truly a multiverse handshake or something equally astonishing. Whatever the answer, this frigid patch of sky reminds us that the cosmos still holds puzzles profound enough to rewrite physics, and perhaps even the story of existence itself. Somewhere in the cosmic void between stars, countless planets wander alone, untethered from any sun's warmth, drifting through eternal night. These are rogue planets, celestial orphans ejected from their birth systems or formed in the frigid isolation of interstellar space. Imagine Earth ripped from the sun's embrace, its oceans freezing over as it careens through the galaxy's dark stretches. Yet for all their bleakness, these rogue worlds might be among the most promising places to hunt for alien life. The violent origins of these nomadic planets read like cosmic survival stories. Most are likely born in ordinary star systems, only to be flung into the abyss by gravitational slingshots during close encounters with sibling planets or passing stars. Others might form directly from collapsing gas clouds too small to ignite into stars, becoming solitary gas giants adrift from their very first moments. The numbers are staggering. Recent microlensing surveys suggest there could be billions more rogue planets in our galaxy than stars, a hidden population outnumbering their star-bound counterparts 20-1. But here's where the story defies expectations. Even without a sun's warmth, some rogue planets could harbor vast subsurface oceans kept liquid by geothermal heat or radioactive decay. Take a super-Earth with a thick hydrogen atmosphere. Its insulating blanket might trap enough internal heat to maintain liquid water beneath miles of ice, just like Jupiter's moon Europa. Microbial life could thrive near hydrothermal vents, drawing energy from chemical reactions rather than sunlight. Some models even suggest certain free-floating worlds could maintain temperate surface conditions for billions of years through atmospheric pressure alone, creating eerie, twilit biospheres under perpetually starless skies. Detecting these dark wanderers is a detective's nightmare. Unlike planets orbiting stars, rogues emit no reflected light and generate almost no heat, making them invisible to traditional telescopes. Astronomers rely on two ingenious tricks to spot them. The first, gravitational microlensing, watches for moments when a rogue planet's gravity briefly bends and brightens the light of a distant star behind it, like a cosmic magnifying glass. The second method hunts for the faint infrared glow of young rogue planets still cooling from their formation. In 2020, astronomers using the European Southern Observatory's telescopes discovered one such world. A lonely Jupiter-sized object roughly 80 light-years away, still warm enough to glow dimly in infrared. The implications rewrite our definition of habitability. If life can persist in the eternal darkness of rogue worlds, then the galaxy's real estate for biology expands exponentially, no longer confined to the narrow Goldilocks zones around stars. Future missions like NASA and Nancy Grace Roman Space Telescope aim to conduct galactic censuses of these nomads, while proposed interstellar probes could one day visit nearby rogue planets, sniffing their atmospheres for biosignatures. Perhaps the most haunting thought, some rogue planets might not be entirely dark. Tidal forces from close encounters with stars could briefly thaw their icy shells, triggering temporary eras of habitability before the cold reclaims them. These fleeting oases might leave behind fossils of alien ecosystems, frozen time capsules adrift between the stars, waiting for some curious traveler to crack them open. Whether barren ice balls or hidden arcs of life, rogue planets challenge everything we thought we knew about where life can take root, and out there in the endless dark, they're rewriting the rules of survival. Far beyond Neptune, in the frozen outskirts of our solar system, a cosmic crime scene unfolds, where the paths of icy objects twist and tilt in ways that defy gravity's expected rules. This is the Kuiper Belt, a sprawling junkyard of primordial space rocks left over from the solar system's birth, and its inhabitants are behaving like they're under the influence of something unseen. Take Sedna, for example, a dwarf planet with a bizarre, stretched-out orbit that takes it over 11 billion miles from the Sun before swinging it back inward, but never close enough to cross Neptune's path. Or consider 2012 VP113, nicknamed Biden, another Kuiper Belt resident with an orbit tilted so sharply it practically loops perpendicular to the solar system's tidy plane. These aren't just random flukes, they're part of a pattern, a celestial breadcrumb trail pointing toward a gravitational mystery, the most tantalizing explanation. A hidden giant planet, 9 lurking in the darkness. The math is compelling. Simulations show that an undiscovered world 5 to 10 times Earth's mass, orbiting about 20 times farther than Neptune, could perfectly explain these orbital oddities. Its gravity would act like an invisible shepherd, nudging smaller objects into clustered, tilted paths over billions of years. The telltale sign: 6 of the most extreme Kuiper Belt objects all point their elongated orbits toward the same patch of sky, like cosmic compass needles aligning toward a magnetic north we can't yet see. Statistically, the odds of this happening randomly are less than 1 in 1,000, suggesting something massive is herding them. Yet Planet 9 isn't the only suspect. Some theorists propose these orbits could be scars from the Sun's chaotic youth, a time when passing stars or the Milky Way's tidal forces might have yanked the outer solar system into disarray. Others wonder if we're underestimating the collective gravity of countless smaller Kuiper Belt objects, their combined pull warping orbits like an invisible hand. There's even a radical idea floating around. What if the culprit isn't a planet at all, but a primordial black hole no larger than a grapefruit left over from the Big Bang? Its gravity could mimic a planet's influence while remaining utterly invisible to telescopes. The hunt for answers is pushing technology to its limits. Telescopes like Subaru in Hawaii scan the sky for faint, slow-moving dots, a painstaking process akin to spotting a single flickering candle in a city the size of Los Angeles. The upcoming Vera Rubin Observatory, with its 3 billion pixel camera, will supercharge this search, mapping the outer solar system in unprecedented detail. Every new discovery tightens the noose, either confirming Planet 9's existence or forcing us to rewrite the rules of celestial mechanics. What's at stake isn't just another planet, it's a potential rewrite of our solar system's history. If Planet 9 is real, it likely didn't form in its current exile. It might be an exiled ice giant flung outward by Jupiter's gravitational bullying during the solar system's violent infancy. Or it could be a stolen world captured from another star during the Sun's birth cluster. Either scenario would mean our cosmic neighborhood was far more crowded and chaotic than we ever imagined. For now, the Kuiper Belt's oddballs keep their secrets, but whether the answer is a hidden planet, a black hole relic, or something even stranger, one thing's clear: the outer solar system is anything but empty. It's a dynamic, mysterious frontier where gravity's rules are still being written, and every peculiar orbit is a clue waiting to crack the case. On August 17, 2017, the universe staged a spectacle so violent it sent ripples through spacetime and lit up the sky with the brilliance of a billion suns. This was JWST 170817, the first ever detected collision of two neutron stars, the densest objects in existence outside black holes. Packing more mass than our Sun into spheres just 12 miles wide, these cosmic corpses whirled around each other hundreds of times per second before smashing together in a cataclysm that forged an entire Earth's weight in pure gold in mere seconds. The event didn't just shake the heavens, it revolutionized how we study the cosmos. What unfolded was a kilonova, a fireworks show of physics unlike anything seen before. As the neutron stars spiraled inward, they stretched and shredded each other's outer layers, flinging debris rich with neutrons into space at nearly light speed. In this extreme environment, atomic nuclei captured free neutrons faster than they could decay, climbing the periodic table to form ultra-heavy elements like gold, platinum, and uranium. For the first time, we had front-row proof that the universe's most precious metals weren't forged in supernova alone, but in these rare, apocalyptic dances of dead stars. The real breakthrough came from how we witnessed it. Gravitational waves from the merger reached Earth first, detected by LIGO and Virgo observatories. 2 seconds later, NASA Fermi satellite caught a gamma-ray burst, a beam of energy so focused it could have sterilized planets halfway across the galaxy had it pointed our way. Then, optical telescopes swiveled to spot the glowing aftermath, a flare of light that faded from blue to red as heavy elements decayed. This trifecta, gravitational waves, light, and gamma rays, marked the dawn of multi-messenger astronomy, where we observe cosmic events through multiple senses simultaneously. It's like listening to an orchestra while watching the conductor, instead of just hearing the music through a wall. The data solved mysteries physicists had debated for decades. The gamma-ray burst's relatively low energy confirmed that short bursts originate from neutron star mergers, not black holes. The light's color revealed the precise cocktail of heavy elements synthesized, matching long-standing predictions about rapid neutron capture or the R process. Even the gravitational waves carried surprises. Their shape hinted that the merged object might have briefly formed a hypermassive neutron star before collapsing into a black hole, a theoretical possibility never before observed. But the implications stretch far beyond astrophysics. Every gold ring on Earth likely began in a cataclysm like this, meaning we're wearing remnants of ancient stellar violence. Future kilonova detections could reveal how frequently these events seed galaxies with life-essential heavy elements without them. Planets like ours might lack the metals needed for technology or even complex biology. Upcoming projects like the Einstein telescope aim to catch these mergers earlier, tracking the neutron star's final orbits to test gravity's laws under extreme conditions. What's haunting is how fleeting these events are. The entire sequence from in-spiral to collision to afterglow unfolds in under a minute. Spotting them requires perfect cosmic choreography, detectors online, telescopes poised, and humanity looking in the right direction at the right millisecond. That we witnessed JWST 70817 at all is a testament to both luck and decades of technological perseverance. Now, with each new merger detected, we're piecing together a clearer picture of how the universe's most exotic matter behaves and how its most precious elements came to be. Something is wrong with the universe's speedometer. For over a century, we've measured how fast the cosmos is expanding, a number called the Hubble constant, using two reliable methods. The first tracks ancient light from the cosmic microwave background, the afterglow of the Big Bang. The second observes pulsating stars and exploding supernova in nearby galaxies. These approaches should agree, like two clocks ticking in perfect sync, but they don't. The discrepancy isn't a minor rounding error, it's a full-blown crisis with measurements diverging by about 9%. This growing conflict, known as the Hubble tension, isn't just a statistical fluke. It's a flashing red light that our understanding of cosmic fundamentals might be missing a crucial piece. The stakes couldn't be higher. If the tension holds, it could mean our standard model of cosmology, the meticulously crafted playbook explaining everything from galaxy formation to the universe's fate is incomplete. One leading theory suggests the existence of dark radiation, an unknown particle flitting through space at near light speeds, subtly altering the expansion rate in the universe's early moments. Others propose that dark energy, the mysterious force accelerating cosmic expansion, isn't constant as we've assumed but evolves over time, growing stronger or weaker in ways we haven't accounted for. The wildest hypothesis, our universe might be lopsided on a scale we've yet to grasp, with expansion rates varying like unevenly rising bread dough. The Hubble tension isn't just academic. It's a detective story with real-world consequences. If dark energy behaves differently than we thought, it could rewrite the universe's expiration date, accelerating its demise or offering unexpected reprieves. New physics might lurk in this discrepancy, waiting to bridge quantum mechanics and gravity. Every time cosmologists refine their measurements using tools like the James Webb Space Telescope to cross-examine distant stars, the tension persists, defying easy fixes. It's as if the universe itself is whispering, "Look closer. There's more here than you've imagined." Whether the answer lies in undiscovered particles, cosmic imperfections, or something entirely outside our theories, one thing's clear: the Hubble tension isn't just a problem to solve. It's an invitation to rethink reality. Beneath the moon's dusty surface lies a hidden network of tunnels, gigantic caverns carved by ancient rivers of lava, their ceilings collapsed in places to reveal gaping skylights. These lunar lava tubes, some wide enough to swallow entire city blocks, aren't just geological curiosities. They might be the golden ticket to humanity's future beyond Earth. Scientists analyzing data from orbiters like NAS, a lunar reconnaissance orbiter, have spotted over 200 of these potential underground passages, their entrances yawning open like subway tunnels abandoned for billions of years. But unlike Earth's lava tubes, which rarely exceed 100 feet across, the moon's lower gravity and lack of erosion have allowed these structures to grow to staggering proportions. Radar scans suggest some stretch for miles, with vaulted ceilings reaching heights rivaling the Eiffel Tower, natural cathedrals waiting to be claimed. The real magic of these tunnels isn't their size, it's what they offer. The moon's surface is a death trap for long-term habitation, bombarded by cosmic radiation 10 times stronger than Earth's and pelted by micrometeorites traveling faster than bullets. Step inside a lava tube, however, and you're suddenly shielded by dozens of feet of solid basalt, a radiation-blocking fortress that also maintains a steady temperature around -20 degrees Celsius, balmy, compared to the surface's 300-degree swings between day and night. Early calculations suggest colonists living beneath this rocky umbrella would experience 500 times less radiation exposure, effectively erasing one of the biggest hurdles to lunar settlement. But the perks don't stop at protection. These tunnels could solve two other existential problems: building materials and water. The same basalt walls that block radiation are rich in iron, silicon, and aluminum, perfect feedstocks for 3D printed habitats or solar panel components. Then there's the ice, shadowed recesses near tunnel entrances, untouched by sunlight for eons, likely trap frozen water delivered by ancient comet impacts. Japan's Selene mission already detected hydrogen signatures, a proxy for water around several tube openings, hinting that pioneers might literally mine their drinking supply from the walls around them. Visionaries at ESA and SpaceX aren't just theorizing, they're prototyping. Robots like Daedalus, a sphere bristling with lasers and cameras, are being designed to rappel into these pits, mapping every crevice before human boots arrive. Meanwhile, architects test inflatable habitats that could line tunnel interiors, creating pressurized cities under natural rock domes, the most ambitious plans. Sealing entire tube sections with transparent polymer membranes, creating sprawling underground greenhouses lit by fiber optic sun pipes channeling surface light. This changes everything. Where we once imagined cramped metal habitats dotting the lunar surface, we might instead have thriving subterranean metropolises, their streets lit by artificial suns, their airlocks opening onto underground farms fed by recycled water. The same tubes shielding us from radiation could become natural particle accelerators, their vacuum-perfect conditions ideal for physics experiments impossible on Earth. And if we master living in the Moon's basement, Mars' far larger lava tubes become the next logical step. What's astonishing is how recent this revelation is. The first definitive evidence of accessible lava tubes only emerged in 2017, when Japan's Kaguya orbiter filmed a 100-yard-wide pit descending into darkness. Now, Artemis missions are already scouting candidate tunnels near the lunar South Pole, where eternal sunlight on crater rims offers solar power just an elevator ride away from subsurface shelter. The Moon isn't just a stepping stone, it's a ready-made ark, its hollow veins waiting to cradle humanity's first off-world civilization. And deep in those silent tunnels, the future might already be written in stone. Hidden in the swirling dance of stars around our galaxy's core lies a butchered cosmic beast, a dwarf galaxy torn apart billions of years ago. Its remains now woven into the very fabric of the Milky Way like celestial scars. Astronomers call it the Gaia sausage, not for its shape, but for the way its stars move, streaking through space on radial, sausage-like orbits that betray their violent past. This discovery, made possible by the European Space Agency's Gaia spacecraft, isn't just a fossil of galactic cannibalism. It's proof that galaxies grow by devouring their neighbors, and that our own Milky Way was a predator long before it became the spiral beauty we recognize today. The Gaia sausage story begins 10 billion years ago, when a dwarf galaxy 1/5 the Milky Way size dared to venture too close. Gravity's inexorable pull stretched and shredded it, dispersing billions of stars into chaotic orbits angled sharply toward the galactic center. Today, these stars still move differently from the Milky Way's native population, like a school of fish swimming against the current. Gaia's precise measurements revealed their telltale motion. Instead of circling the galactic disk in orderly spirals, they plunge inward and outward like comets, their paths tracing the aftermath of an ancient collision. What makes this discovery revolutionary is how it reshapes our origin story. Before Gaia, astronomers assumed the Milky Way grew mostly by gentle mergers absorbing gas and small star clusters over time. The Gaia sausage suggests otherwise. Our galaxy's adolescence was marked by brute force, a dramatic smash-up that fundamentally altered its structure. Simulations show this merger could have thickened the Milky Way's disk, scattering stars into the puffy halo we see today. It might even have triggered bursts of star formation, seeding the cosmos with new suns born from the turmoil. But the revelations don't stop there. The sausage stars are chemically distinct, older and poorer in heavy elements like iron compared to the Milky Way's native population. This fingerprint reveals their origins in a smaller, less evolved galaxy where fewer supernovae had enriched the stellar nursery with metals. Some of these stars now orbit perilously close to our supermassive black hole, Sagittarius A, their presence hinting that the dwarf galaxy's core might have contributed to the black hole's growth during the merger. The implications ripple far beyond our galaxy. If the Milky Way's growth involved such violent encounters, then galaxy formation across the universe must be far more chaotic than our pristine models suggested. The Gaia sausage might just be the first of many ghost galaxies we uncover hidden in plain sight, their stars camouflaged among the Milky Way's billions until precise motion tracking exposes their alien heritage. Future telescopes like the Nancy Grace Roman Space Telescope will hunt for similar stellar streams in other galaxies, piecing together a universal narrative of cosmic predation. What's haunting is the scale of time involved. The Gaia sausage stars have orbited our galaxy for twice as long as Earth has existed, their paths frozen in the gravitational amber of that primordial collision. They're the ultimate survivors, celestial refugees from a time when the Milky Way was young and hungry. And as we map more of these stellar ghosts, we're not just reconstructing a single event, we're reading the autobiography of the universe itself, written in the trajectories of stars that refuse to forget. Galaxies aren't just drifting apart as the universe expands, they're racing toward something. In 2008, astronomers poring over cosmic microwave background data stumbled onto a phenomenon so unsettling it earned the name dark flow. Hundreds of galaxy clusters, each containing thousands of galaxies, are moving in unison toward a single point beyond the observable universe, as if tugged by an invisible hand. This isn't just random motion, it's a coordinated march toward an unseen attractor so massive that its gravity defies everything we know about cosmic structure. The implications shatter conventional cosmology. According to Einstein's theories, the universe's expansion should dilute gravitational influences over vast distances. Nothing within the observable cosmos, not even superclusters, should wield enough gravity to orchestrate this motion. Yet the data collected by NASA's Wilkinson Microwave Anisotropy Probe shows clusters streaming at speeds exceeding 2 million miles per hour toward a void between the constellations Centaurus and Vela. It's as if the universe itself is tilted, with galaxies sliding down a slope we can't see. Theories to explain this anomaly range from revolutionary to downright surreal. One camp argues for flaws in our measurements, perhaps residual errors in how we subtract the Milky Way's motion from cosmic background data. But the signal persists even in refined analyzers, ruling out simple calibration glitches. More daring explanations suggest the attractor could be a supercluster of unimaginable scale. A structure so vast it extends beyond the cosmic horizon, its gravity leaking into our observable bubble. Then there's the spine-tingling possibility. Dark flow might be evidence of other universes. In multiverse theories, our cosmos is one bubble in an infinite foam of universes, each with different physical laws. If a neighboring bubble brushed against ours during inflation, its gravitational pull could have imprinted this preferential direction on our galaxy clusters, like a magnet tugging iron filings through paper. Critics counter that such an idea is untestable by definition, since anything beyond our cosmic horizon is forever out of reach. But supporters point out that dark flow's alignment with certain anomalies in the CMB, like the infamous cold spot, a hint at a deeper connection. Practical consequences ripple closer to home. If dark flow is real, it could mean our local universe is far more asymmetric than we thought, with matter distributed unevenly on scales we've yet to map. Future telescopes like ESA's Euclid will test this by measuring galaxy motions with unprecedented precision, hunting for subtle deviations that might reveal the attractor's nature. For now, dark flow remains one of cosmology's great open questions, a reminder that even as we peer deeper into space, the universe keeps its most profound secrets just beyond the edge of sight. Whether it's a shadow of something unimaginably vast or a flaw in our understanding of gravity, one thing is certain: the cosmos still has the power to unsettle, challenge, and inspire. 55 Cancri E isn't just another exoplanet, it's a cosmic jewelry box orbiting a star 40 light-years away, and its contents might be more dazzling than any sci-fi treasure. Twice Earth's size but 8 times its mass, this world's density suggests something extraordinary. Beneath its scorching 2,000 degrees Celsius surface could lie a layer of diamond hundreds of miles thick, forged in a stellar pressure cooker of unimaginable heat and pressure. How does a planet turn into a celestial gemstone? The secret lies in its chemistry. Most rocky planets, like Earth, form from silicon and oxygen-rich materials, creating familiar landscapes of basalt and granite. But 55 Cancri E orbits a carbon-rich star, bathing its formation in an environment where carbon outnumbers oxygen. Under such conditions, carbon atoms bond into crystalline structures, graphite at lower pressures, diamond at higher ones. Simulations suggest this world's interior could be a diamond factory, with carbon compressed into glittering lattices under pressures 1,000,000 times greater than Earth's atmosphere. Even its mantle might resemble a diamond-encrusted ocean, with carbon compounds like silicon carbide crystallizing into abrasive, gem-like particles. Yet this planet's extremes don't stop at its composition. Its orbit is so tight 18 times closer to its star than Mercury is to the Sun, that a year lasts just 18 hours. Gravitational locking ensures one side permanently faces the star, creating a blistering day side hot enough to vaporize metals and a night side where temperatures might allow diamond rain to form in the atmosphere. Telescopes have even detected signs of an exotic carbon-based haze shrouding the planet, possibly rich in compounds like acetylene or hydrogen cyanide. This discovery shatters traditional planet classifications. 55 Cancri E defies labels like super-Earth or gas dwarf. It's something entirely new, a carbon-dominated world rewriting the rules of planetary science. If Earth is a water world, this is its antithesis, a desiccated, diamond-encrusted relic of stellar alchemy. The existence of such planets hints at a staggering diversity in cosmic chemistry. Around carbon stars, entire systems might harbor carbon-based planets with tar-like oceans or mountains of silicon carbide, landscapes straight out of planetary science fiction. What's next? Instruments like the James Webb Space Telescope could analyze 55 Cancri E's atmosphere for carbon monoxide or methane, clues to its diamond-bearing potential. Meanwhile, astronomers are hunting for other carbon-rich worlds, wondering if they're rare curiosities or hidden gems in the galactic catalogue. One thing's certain, the universe's creativity knows no bounds, offering worlds so extreme they challenge not just our definitions, but our very imagination. Stretching across a mind-numbing 330 million light-years, the Boötes Void isn't just an empty patch of sky. It's a cosmic desert so vast you could fly our entire Milky Way across it 30,000 times before hitting anything substantial. Discovered in 1981 by astronomer Robert Kirshner, this staggering absence of galaxies defies everything we know about the universe's structure. While most of space resembles a sponge with galaxies clustered along dense filaments, the Boötes Void flips the script, a spherical chasm of near-nothingness containing only 60 galaxies where thousands should exist. It's as if someone took a cookie cutter to the cosmos, leaving behind a hole so gigantic it challenges our understanding of how matter organizes itself. What carved this void? One leading theory points to the aftermath of a feeding frenzy among smaller voids. Picture multiple cosmic bubbles expanding and merging over billions of years, their combined growth pushing galaxies outward like a gravitational tide receding from shore. Another possibility involves dark energy, the mysterious force accelerating the universe's expansion, acting unevenly, stretching certain regions into barren wastelands faster than galaxies can form. Then there's the spine-tingling alternative. The Boötes Void might be the imprint of an unfathomably ancient collision with another universe, a bruise left by a multiverse-scale event we can barely comprehend. But the real shocker, this void isn't unique. Surveys now suggest the cosmos is speckled with similar emptiness, like holes in Swiss cheese, each revealing how little we grasp about gravity's large-scale behavior. Some voids even appear to be underdense to the point where space itself might expand slightly faster within them, a phenomenon that could rewrite dark energy's playbook. The galaxies trapped inside the Boötes Void tell their own eerie story. Isolated and starved of neighbors, they evolve in profound isolation, their starlight stretching across millions of light years without another galaxy to interrupt the darkness. Astronomers call them red and dead, elderly galaxies whose star-forming gas was stripped away eons ago, leaving behind relics that glow like embers in a dying fire. Studying these loners offers clues about how environment shapes galactic fate, proving that even in the universe's emptiest corners, there's drama unfolding on cosmic timescales. For cosmologists, voids like Boötes aren't just curiosities, they're stress tests for our theories. If dark matter and dark energy behave as we think, their gravitational interplay should create voids of predictable sizes and distributions. Yet the scale of Boötes straddles the edge of statistical plausibility, hinting that our models might be missing a crucial piece. Upcoming telescopes like the Vera-Rubin Observatory will map millions more galaxies, probing these cosmic deserts for answers. The Boötes void does more than unsettle our equations, it redefines emptiness itself. This isn't passive nothingness, it's an active, evolving entity that shapes the universe as surely as galaxies do. And somewhere in its vast, silent expanse, the cosmos might be whispering secrets about forces we've yet to name. Our solar system isn't just floating helplessly through the galaxy, it's cocooned in an invisible shield, a vast protective bubble blown by the sun itself. Known as the heliosphere, this teardrop-shaped force field stretches more than twice as far as Pluto's orbit, created by the constant stream of charged particles we call the solar wind. Picture the sun exhaling a 1,000,000-mile-per-hour breeze of protons and electrons, their outward pressure pushing against the interstellar medium like a cosmic windshield against the void. This isn't just empty space, it's a battlefield where solar and stellar winds collide. The heliosphere's edge, called the heliopause, marks where our sun's influence wanes and the Milky Way takes over. Here, particles from the sun crash into interstellar gas and dust, creating a turbulent boundary layer that Voyager 1 and 2 crossed in 2012 and 2018 respectively, becoming the first human-made objects to enter interstellar space. Their readings revealed something astonishing. The heliosphere isn't static. It pulses and breathes with the sun's 11-year activity cycle, expanding when solar storms rage and contracting during quieter periods. What does this mean for Earth? The heliosphere is our first line of defense against galactic cosmic rays, high-energy particles from exploded stars that would otherwise bombard our atmosphere. During periods when the heliosphere weakens, studies link increased cosmic ray flux to cloud formation changes and even shifts in lightning patterns. There's evidence suggesting these subtle variations might influence climate cycles over millennia, though the mechanisms are complex. When the heliosphere contracts during solar minima, more cosmic rays sneak through, potentially seeding low-altitude clouds that reflect sunlight back to space. Conversely, a robust heliosphere during solar maxima might subtly warm the planet by blocking these particle showers. The heliosphere's shape adds another layer of mystery. As our solar system orbits the galaxy, it plows through interstellar space like a ship through water, creating a bow shock ahead and a trailing tail. Data from NASA Interstellar Boundary Explorer satellite reveals this tail isn't straight, it's split into multiple swirling lobes, shaped by the interplay between the sun's magnetic field and interstellar gas flows. Some models suggest passing through denser interstellar clouds could dramatically compress the heliosphere, potentially exposing inner planets to higher radiation levels, a scenario that may have occurred multiple times in Earth's history, leaving isotopic traces in ancient ice cores and tree rings. Understanding this invisible shield has never been more crucial. As we plan crewed missions to Mars, knowing how heliosphere changes affect radiation exposure could mean the difference between life and death for astronauts. Future probes like the proposed Interstellar probe aim to map the heliosphere's full three-dimensional structure, while advanced simulations unravel how its fluctuations might have guided the evolution of life on Earth. One thing's certain: the sun's reach extends far beyond light and warmth. It carves out a safe harbor in the cosmic sea, and its invisible currents might just shape our planet's destiny in ways we're only beginning to understand. The James Webb Space Telescope didn't just open a new window on the cosmos, it shattered the glass entirely. Within months of its first images, this revolutionary instrument began serving up discoveries so profound they're forcing scientists to revisit decades of cosmic assumptions. Take those 6 massive galaxies spotted in the telescope's early data, each weighing as much as 100 billion suns, yet existing when the universe was barely 3% of its current age. According to standard models, structures this enormous shouldn't have had time to form so soon after the Big Bang. It's like finding a skyscraper in the ruins of the Stone Age, defying every construction timeline we've established. These galaxies aren't just old, they're freakishly mature, filled with red, dust-obscured stars that indicate rapid, early growth spurts. One particularly shocking example, dubbed the Sparkler Galaxy, appears to be surrounded by globular clusters, dense groupings of ancient stars that look nearly as old as the universe itself. This flies in the face of conventional wisdom, which assumes galaxies grew gradually through mergers over billions of years. Webb's infrared eyes reveal a different story. Some structures might have formed almost instantaneously by cosmic standards through processes we're only beginning to comprehend. The anomalies don't stop there. Webb has spotted supermassive black holes in the early universe that are far too large for their age, some weighing billions of solar masses when they should still be stellar-sized infants. One leading theory suggests these cosmic behemoths might have formed directly from collapsing primordial gas clouds, skipping the star phase entirely. Others speculate they're evidence of exotic physics, like wormholes funneling matter from other universes into ours. Either scenario would rewrite chapters in astrophysics textbooks. Perhaps most mind-bending are the chemical fingerprints Webb has uncovered in these ancient galaxies. Spectroscopic analysis reveals heavy elements like oxygen and nitrogen existed much earlier than predicted elements forged in stellar furnaces and scattered by supernova. This implies the first stars must have lived fast and died violently, seeding the cosmos with life-essential atoms before our models say they should have. Some of these early galaxies even show potential signs of water vapor, hinting that the building blocks for habitable worlds were present astonishingly soon after the universe's birth. What's truly revolutionary is how Webb achieves these breakthroughs. Unlike Hubble, which sees mainly invisible light, Webb specializes in infrared, allowing it to peer through cosmic dust and detect light stretched into longer wavelengths by the universe's expansion. This lets the telescope function as a time machine, capturing photons emitted over 13 billion years ago. Its segmented, gold-coated mirror, 21 feet across, gathers 7 times more light than Hubble, revealing details 50 times fainter. The telescope's discoveries are already reshaping fundamental questions about cosmic dawn. Did galaxies form differently than we thought, perhaps through collapse of vast, dark matter pancakes? Could the early universe have hosted unknown, ultra-efficient star-forming processes? Each new Webb image chips away at our assumptions, painting a picture of cosmic youth that's far more dynamic and complex than anyone imagined. Future observations promise even deeper revelations, potentially uncovering population 3 stars, the hypothetical first generation of stars made purely of hydrogen and helium, or catching galaxies in the act of igniting the universe's first light. For now, Webb's early findings stand as both triumph and provocation, a reminder that the universe rarely follows our tidy timelines. Every ancient galaxy it unveils isn't just a scientific specimen, it's a challenge to rethink how cosmic history unfolded. And with years of observation still ahead, the biggest revelations may be yet to come. From hidden oceans on distant moons to rogue planets drifting through the void, these 30 discoveries aren't just rewriting textbooks, they're reshaping humanity's future. Imagine medical breakthroughs inspired by extremophiles in Enceladus plumes, or unlimited energy harnessed from the quantum chaos of black holes. Picture cities thriving beneath lunar lava tubes, shielded from radiation by nature's architecture, or climate solutions reverse-engineered from Martian atmospheric chemistry. Each revelation peels back another layer of cosmic possibility, proving that the universe isn't just a spectator, it's an active participant in our evolution. Consider the practical revolutions already unfolding. Gravitational wave astronomy is refining earthquake prediction models by studying space-time ripples from neutron star collisions. Quantum insights from quasars are accelerating superconductor research, promising lossless power grids. Even the humble tardigrade, surviving the vacuum of space, is revolutionizing vaccine storage. And these are just the first whispers of transformation. Wait until we tap into dark matter's gravitational secrets or decode the origin of life from Europa's icy geysers. But beyond technology, these discoveries confront us with existential truths. The Fermi paradox asks if we're alone or doomed. The Hubble tension hints at physics beyond Einstein. The cold spot whispers of parallel realities. Together, they dissolve the line between science and philosophy, forcing us to grapple with our fragile, extraordinary place in the cosmos. Stay with us as this story unfolds. Hit subscribe to journey together through the next chapters, because when the James Webb Telescope spots its next anomaly, when astronauts drill into Mars methane vents, when LIGO catches gravitational waves from the Big Bang itself, you won't just be watching history. You'll be part of the generation that turned these cosmic mysteries into humanity's stepping stones. The universe is speaking. All we have to do is keep listening.